Welcome, curious minds, to the deep dive. Today we're plunging into, well, a really fascinating concept that has captured humanity for centuries. The inner Earth. This idea of a world hidden right beneath our feet, a secret realm. It pops up everywhere, from ancient myths to really fantastical stories.
It's amazing how persistent it is, isn't it? And, it wasn't just folklore. Way back in 1692, Edmund Halley.
Wait, the Halley. Halley's Comet Halley.
That's the one, the astronomer. He actually proposed that Earth might be made of concentric hollow shells.
Okay, hold on. Halley, a serious scientist. Why on earth, literally, would he suggest something that sounds so well out there?
Well, his reasoning, believe it or not, was pretty scientific for the time. He was trying to make sense of some genuinely puzzling real-world data.
Like what?
Things like compasses behaving strangely, or why the magnetic poles seem to drift. He even speculated that gases escaping from these inner shells could be causing the aurora borealis. So back then, it wasn't seen as totally fringe. It was a serious attempt, though obviously wrong, to explain things they couldn't otherwise explain.
So he put it on the table, scientifically speaking.
Yeah.
But it seems like the idea kind of took on a life of its own after that, way beyond science.
Oh, absolutely. You had figures like John Cleves Sims Jr., an American Army officer who became this passionate campaigner for expeditions. He wanted to find openings at the poles.
Did they actually go look at?
His advocacy did help inspire a major expedition, the Great United States Exploring Expedition of 1838. Spoiler, they didn't find an entrance to the inner Earth.
Shocker.
Right. But here's where it gets really interesting. Fiction, that's what really cemented the hollow Earth in our collective imagination. You had Ludwig Holberg's Niels Klim's Underground Travels in 1741.
Never heard of that one.
It imagined a whole solar system inside the Earth. And then, of course, decades later, Jules Verne's Journey to the Center of the Earth in 1864. Those stories just made the idea stick, long after science had basically said, nope, not possible.
And that's pretty much our mission today, right? We're going to use what we know now, the modern science, to really deconstruct this hollow Earth myth.
Exactly.
We'll look at the real limits of underground spaces, uncover the truly astonishing life that does exist deep down, and then really pick apart why a complex civilization couldn't actually survive there.
And finally, kind of flip it around. Look at how this whole inner world idea connects to the search for life, not here, but maybe under the surface of other planets or moons.
Okay, so first things first. The scientific consensus today. Pretty clear-cut.
Oh, completely. To put it bluntly, the hollow Earth theory is just unequivocally contradicted by, well, everything we know. Decades, centuries even, of precise measurements. A planet is dense, it's dynamic, and it's definitely solid.
Okay, so if it's not hollow, what is down there? Give us the tour of the real Earth interior.
Right, so think of it like an onion, layers all the way down. What we live on, that's the crust. It's super thin and brittle, relatively speaking, maybe 5 to 10 kilometers thick under the oceans, but up to, say, 70 kilometers under continents.
Just the skin, basically, what's underneath.
Below that, you've got the mantle. This is the big one. Extends down almost 2,900 kilometers, makes up something like 84% of Earth's volume.
Wow.
It's mostly silicate rock. And here's the cool part. Even though it's solid, the intense heat and pressure down there mean it actually flows, like incredibly thick honey, but over millions of years.
And that's what moves the continents, plate tectonics.
That's the engine right there. That slow churn drives plate tectonics, builds mountains, causes earthquakes. Everything happening on the surface is linked to this deep flow.
Okay, mantle, and then we get to the core.
Exactly. 2 parts. First, the outer core. That's a sphere of liquid iron and nickel, about 2,200 kilometers thick.
Liquid metal.
Yep. And it's churning, convecting. That motion is what generates Earth's magnetic field. It's like a giant dynamo. That's the geodynamo theory.
Okay, the magnetic shield. Got it. And then right at the very center.
The inner core. Another ball, about 1,200 kilometers in radius, also iron and nickel. But this one's solid.
Solid. But isn't it incredibly hot down there? Like, hotter than the sun's surface?
It is. Hotter than the surface of the sun, yeah. But the pressure, it's just astronomical. Over 3.6 million times the pressure at the surface. That immense pressure overrides the temperature and forces the iron and nickel into a solid state.
Mind-boggling. So this layered structure, crust, mantle, liquid outer core, solid inner core, that leaves absolutely no room for Halley's hollow shells.
Not a bit. The model is really well defined.
Okay, this sounds super detailed. But how do we know all this? We haven't exactly drilled down there, right?
Yeah.
What's the smoking gun against a hollow Earth?
Right, no drilling. Our main tool, our sort of X-ray vision into the Earth, Comes from seismic waves, you know, the waves generated by earthquakes.
Ah, like P waves and S waves. I remember those from school.
Exactly. P waves are compressional. They can travel through solids and liquids, but S waves, the shear waves, they cannot travel through liquids. It's like trying to shake a rope that's loose, the wave just dies. And what we see consistently every time there's a big earthquake is that S waves travel through the mantle, but they get completely blocked by the outer core. They hit it and stop. That's definitive proof it's liquid.
Ah, the S-wave shadow zone.
Precisely. But then we detect P waves going through the outer core, hitting the inner core, and S waves can actually travel through the inner core, proving it's solid.
So the waves map it out for us.
They do. By measuring how long these waves take to travel through different paths, geophysicists can build up an incredibly detailed picture of the interior. Density, temperature, state. There's just no place for huge empty voids.
That seems pretty airtight. Anything else?
Oh, yeah. Simple density and gravity. This is a really fundamental one. Earth's average density is about 5.5 grams per cubic centimeter.
Okay.
But the rocks right here on the surface, they're much lighter, maybe 2.75 GC meter Rossiter. If the Earth were hollow, its overall density would have to be even lower than surface rocks.
Right, because it would be mostly empty space.
Exactly. But our planet is heavy. Its mass and the strong gravity it exerts, they absolutely require an incredibly dense core, something much, much denser than rock. That points directly to iron and nickel under immense pressure down there, maybe 10 to 13 GC meter.
And people figured this out a long time ago.
They did. Calculations challenging the hollow idea based on density go way back to the 1700s. Pierre Bouguer, Charles Hutton's experiments on Chehallion Mountain, Henry Cavendish weighing the Earth. This isn't new stuff.
So the math just doesn't work for a hollow planet.
Not even close. And then there's just basic physics of how planets form. Gravity pulls stuff together. The most stable shape for a big blob of self-gravitating stuff is a solid sphere, or layers within a sphere.
Makes sense.
And think about the pressure, the sheer weight of all the rock above what we call lithostatic pressure. It's immense. Any large void would simply collapse under its own weight. Rock isn't strong enough to support a planet-sized hollow shell against gravity. It would just get crushed.
Okay, and you mentioned the magnetic field earlier. Halley thought that was evidence for his idea.
He did, ironically. But our modern understanding, the geodynamo theory, absolutely requires that churning, liquid, metallic outer core to generate the field. A hollow structure just can't do that.
Right.
And same goes for geology. Plate tectonics, mountain building, volcanoes. These are all surface expressions of a dynamic, hot, convecting mantle. None of that makes sense in a static, hollow planet.
It's just fascinating, this disconnect. Science had pretty much debunked it centuries ago, right?
Yeah, Halley proposes it in 1692. Serious refutations start less than 50 years later, and the case is basically closed scientifically by the early 1800s.
But that's when it really takes off in popular culture.
Yeah.
With Sims and Verne and all that.
Exactly. Its popularity surged after it was scientifically disproven. It just goes to show, once an idea captures the imagination, it becomes a good story. Facts sometimes take a backseat. It becomes a cultural trope, independent of reality.
Okay, so planet Earth, definitely not hollow, case closed. But that leads to the next question, doesn't it? What about natural caves? Could any real underground voids be big enough to, say, hide a lost civilization? What's the actual scale of the underworld?
That's a much more plausible question, moving from sci-fi to geology. And to answer it, we need to understand how big caves actually form speleogenesis.
Okay.
Most of the world's really large cave systems are what we call solution caves. They form in specific rock types, mainly limestone, in areas called karst landscapes.
How does that work? Water dissolving rock.
Pretty much. Rainwater picks up carbon dioxide from the air and soil, forming a very weak carbonic acid. This slightly acidic water seeps into cracks in the limestone. Over vast timescales, millions of years, it slowly dissolves the rock along these fractures, widening them into passages, chambers, and eventually huge interconnected systems.
It's amazing what water can do over time. So what are the record holders, the biggest ones we know of?
Well, for the longest cave system, that's Mammoth Cave in Kentucky, USA. It's got an incredible 426 miles, that's 686 kilometers of mapped passageways.
Whoa, that's enormous.
It is, formed over maybe 10, 15 million years. Yeah. But crucially, it's not one giant open space. Think of it like a massive, tangled, three-dimensional maze spread across multiple levels. Lots of tunnels, not one big room.
Right, so length isn't volume. What about the biggest single chamber? like a cathedral underground.
For that, you go to Sonong Cave in Vietnam. It has the largest known single cave passage by volume anywhere on Earth.
How big are we talking?
The main passage is over 5 kilometers long, and parts of it are just colossal, over 200 meters high and 150 meters wide.
That's hard to even picture. Like skyscrapers could fit inside.
Pretty much. It's so vast it has its own river flowing through it, even its own jungle ecocenter in areas where the roof is collapsed and sunlight gets in. Those collapses are called dolines. Sunong really pushes the limits of what a single, stable, natural void can be.
Okay, those are definitely impressive. But still, 150 meters wide. When you think about a city or a civilization, are there hard geological limits stopping them from getting even bigger?
Absolutely. Even these giants run into fundamental constraints. The big one is that crushing rock pressure, the lithostatic pressure we talked about earlier.
Right, the weight from above.
As you go deeper, it just becomes too much. It's generally thought that stable open voids simply can't exist much deeper than about 3,000 meters, maybe 10,000 feet. Below that, the rock just behaves more like plastic and flows, closing any openings.
So depth is a major limiter.
A hard limit. And then there's just structural integrity. How wide can a natural rock ceiling span before it collapses under its own weight? That depends on the rock type, fractures, water. But even in Sonorong's case, that enormous 150-meter width is likely close to the maximum possible for that kind of limestone formation.
And the process itself limits the size.
Yeah, it's kind of a catch-22. The very process of dissolution that creates the cave also weakens the surrounding rock. As the void gets bigger, the roof gets less stable, making collapse more likely. It's a self-limiting process in many ways.
Okay, so geology puts some pretty firm caps on cave size. How does that stack up against what a hypothetical underground civilization would actually need?
This is where the idea really falls apart, scale-wise. Let's try to compare. Remember the Biosphere 2 project?
Yeah, the giant terrarium in Arizona, that didn't go so well, did it?
Not exactly. It cost $200 million, enclosed about 1.27 hectares, that's roughly 3 acres for just 8 people. And they couldn't keep the air stable or grow enough food for their 2-year mission. It was a failure in terms of being self-sufficient.
Okay.
Now, some analyses suggest that for a truly stable, long-term, closed ecosystem for even a small human population, you might need an area closer to, say, 100 square kilometers.
100 square kilometers. And Sundong, the biggest single chamber you said its floor area was?
Roughly 0.75 square kilometers. Less than 1% of what might be needed for even a tiny, stable population's life support system.
Wow. Not even close.
Not even in the same ballpark. Mammoth Cave's huge length doesn't help. It's a network of tunnels, not usable living or agricultural space.
Yeah.
Geological processes simply cannot create a single stable void anywhere near the scale needed for a self-sufficient human biosphere. The mismatch is just unbridgeable.
Okay, so subterranean human civilization is definitely off the table geologically, but you mentioned astonishing life does exist deep down. What's the reality there? Who are Earth's real underground inhabitants?
Now this is where reality gets, I think, even more amazing than the fiction. For a long time, we really thought life was mostly a surface phenomenon, right? Photosynthesis, sunlight.
Yeah, basics.
But then came projects like the Deep Carbon Observatory. This massive global effort completely changed our view. They discovered what's now called the deep biosphere.
Deep biosphere sounds intriguing.
It is. It's a vast ecosystem of microbial life, mostly bacteria and archaea extending kilometers down beneath the continents and the seafloor.
Kilometers, wow. How much life are we talking about?
Get this. The estimated biomass, the sheer amount of carbon tied up in these deep microbes, is somewhere between 15 and 23 billion tons. Billion with a B. That's potentially 250 to 400 times more carbon biomass than in all humans combined. It's arguably the biggest ecosystem on the planet, and we've barely scratched the surface of exploring it. Think of it as a subterranean Galapagos.
That's absolutely wild. But how? How do they live down there in total darkness, crushing pressure, no obvious food?
The key is chemosynthesis. Forget photosynthesis, there's no sunlight. These microbes are chemists. They make a living by harnessing energy from chemical reactions.
Chemical reactions?
Yeah.
With what?
They oxidize inorganic compounds found in the rocks or fluids down there. Things like hydrogen sulfide, that rotten egg smell, methane, hydrogen gas, even dissolved metals like iron. They use the energy released from these reactions to fix carbon dioxide into organic matter, just like plants do with sunlight. They form the base of entire food webs, completely independent of the sun.
That's incredible, like a whole separate life system?
Yeah.
Are there any, showcase examples, places where we can really see this in action?
The absolute classic, the poster child for this, is Movile Cave in Romania.
Movile Cave. Okay. What's special about it?
It was discovered by accident in 1986, and it turns out it had been completely sealed off from the outside world by layers of impermeable clay for, wait for it, an estimated 5.5 million years.
5.5 million years.
It's
sealed off.
Completely isolated, no energy from the sun, no organic matter washing in, nothing from the surface for millions of years.
Okay, that's properly mind-boggling. So what's it like inside? What kind of life could possibly survive that long in isolation?
Well, first off, the atmosphere is toxic for us. Very low oxygen, high carbon dioxide, and rich in hydrogen sulfide and methane bubbling up from geothermal groundwater.
Sounds delightful.
Right. But the entire ecosystem runs on it. The base of the food web is these thick, floating mats of chemotrophic bacteria. They're oxidizing that sulfide and methane for energy.
And what eats the bacteria mats?
A surprisingly diverse community of invertebrates, creatures without backbones. They've found over 50 species in there. Things like unique blind leeches, spiders, pseudoscorpions, little crustaceans called isopods. Even the world's only known cave-adapted water scorpion.
Water scorpion, wow. Are these species found anywhere else?
Many aren't. At least 37 of the species identified in Morville Isle are endemic. They exist nowhere else on Earth. They evolve right there in isolation. There's even an apex predator, a venomous centipede called Cryptops speleorex, the king of the cave.
Okay, that is like something from a movie. How do they manage in the dark?
They show classic cave adaptations, what scientists call trogloomorphism. They've lost their eyes completely. They've lost all skin pigment. And to compensate, they've evolved incredibly long antennae and other sensory appendages to navigate and hunt using touch and chemical cues in the pitch black.
So they're extremophiles, basically.
Absolutely. Movable cave life and the deep biosphere microbes in general are textbook extremophiles. They thrive in conditions that would kill us instantly. We find life near deep-sea vents at 122 degrees Celsius in sub-zero Antarctic lakes, under pressure 1,100 times higher than at sea level in the Mariana Trench, in battery acid conditions, highly alkaline waters, even environments blasted with radiation. Life finds a way, but it adapts.
Okay, so Movable Cave is amazing. It proves life can hang on for millions of years without the sun. But doesn't this kind of argue against the idea of an advanced underground civilization?
It creates a huge paradox for that idea, exactly. Movable proves life's tenacity, its ability to use chemosynthesis. However, look at the kind of life that evolved there over 5.5 million years in isolation.
Microbes and weird bugs.
Exactly. Microbes and small, specialized invertebrates, what didn't evolve. Large size, complex brains, intelligence, technology. Why? Because those things are incredibly energy expensive. A human brain uses something like 20% of our entire energy budget. That kind of metabolic cost is an evolutionary luxury. It's really only feasible in environments rich in easily accessible energy, like surface ecosystems powered ultimately by a star through photosynthesis. Movable Cave is the perfect natural experiment showing what long-term evolution in a dark, energy-poor environment tends to produce. Life? Yes. Complex intelligence? Apparently not. The energy just isn't there to support it.
Right. So the very evidence for life deep underground also kind of undermines the fantasy of complex life down there.
Precisely. Life is possible, but its complexity seems fundamentally limited by the available energy budget in those environments.
Okay, so natural caves aren't big enough, and the kind of life that can survive deep down isn't building cities. What about engineering? Could we build a civilization underground? Let's do the thought experiment. Humans decide to go subterranean for millennia. Can it work?
It's a fascinating thought experiment, but when you really dig into the science and engineering, it collapses. It runs into a series of interconnected, basically unsolvable problems, mostly related to thermodynamics and system dynamics.
Okay, break that down. What's the first hurdle?
Any long-term, isolated habitat space station, moon base, underground city has to be a closed ecological life support system, a CELSS.
Meaning everything gets recycled.
Perfectly. Air, water, food, waste, all mass has to be perpetually recycled within the system. The only thing that can really come from outside is energy.
And we already mentioned Biosphere 2 as a kind of failed attempt at that.
A profoundly cautionary one, yes. Multi-million-dollar project, huge facility for just 8 people, and they couldn't keep the basics stable for even 2 years. It just highlights the staggering complexity. And its instability was probably worsened by its relatively small size. Scaling that up to a civilization. Geologically impossible space requirements aside, the system dynamics become exponentially harder.
So just keeping people alive, basic life support, is hurdle number 1. What else goes wrong in this thought experiment?
You run into what you could call a cascade of biologistical failures. problems that compound each other. Take the air. Thousands, millions of people breathing. They produce enormous amounts of CO2.
Right.
On the surface, oceans and plants handle it. Underground, you need massive industrial-scale scrubbers constantly removing CO2 and somehow replenishing oxygen. Biosphere 2 couldn't even get that balance right for 8 people. Plus, CO2 is heavier than air. It would pool in low-lying areas, creating lethal pockets. You'd need huge, energy-hungry ventilation systems constantly running with countless points of failure.
Okay, air is a nightmare. What about food?
No sunlight.
Exactly. All agriculture would have to be artificial. Think vast hydroponic or aeroponic farms under intense grow lights. The energy demand would be absolutely astronomical, continuous, and non-negotiable.
And probably risky, right? Relying on just a few crop types. Hugely risky. You'd inevitably end up with fragile monocultures. One disease, one pest adapted to your system, and your entire food supply could collapse catastrophically.
Okay, air, food, this all points to energy. Where does that come from, and what are the problems there?
This is maybe the biggest killer, the thermodynamic trap. Realistically, the only long-term energy sources down there are geothermal or nuclear. Both have massive, potentially insoluble problems in a closed system.
Which are?
Problem 1, waste heat. Basic physics, the second law of thermodynamics. Every single energy process, every light bulb, every computer, every machine generates waste heat.
Sure.
On the surface, that heat radiates away into space. In a sealed underground cavern, it has nowhere to go, just builds up relentlessly. Every joule of energy used eventually becomes heat trapped inside the habitat. You literally cook the place over time.
Oh, that's bad. What's the second problem? Nuclear.
Radioactive waste. If you use nuclear reactors, you produce spent fuel that's incredibly dangerous for thousands, tens of thousands of years. On the surface, we argue about burying it deep underground, in a closed subterranean habitat, whereas away, there isn't one.
So you'd have to store it inside with everyone.
You'd have to store this lethal accumulating waste within the living space indefinitely. It's an ever-expanding zone of permanent contamination, a guaranteed hazard for every future generation trapped in there.
Okay, heat and radioactive waste. Those sound like deal breakers. What about just keeping the technology running for centuries, millennia?
Another nightmare. Think about how often stuff breaks now. NASA's studies for even short space missions suggest needing spare parts equal in mass to the original systems for high reliability for millennia. That's meaningless.
So they'd have to make everything themselves.
Everything, every screw, every wire, every computer chip, every O-ring. That means a complete industrial base, mining the rock around them, refining ores, smelting metals, fabricating complex components, all underground.
Which uses more energy.
Exactly. It consumes vast energy, generates more waste heat, produces more toxic industrial waste, which also has nowhere to go, and rapidly depletes whatever finite mineral resources exist within their sealed cavern.
It's a loop, a death spiral almost.
It's a completely self-defeating loop. The technological solutions needed to meet the biological needs create even more complex technological and thermodynamic problems, which require more solutions, generating more heat and waste. It leads to inevitable long-term system collapse. It's not if, it's when.
Okay, even if, purely hypothetically, some super engineers could solve all that.
Yeah.
What about the people? Could humans even cope with living like that for generations?
This might be the final nail in the coffin. Even if the engineering was magic, the humans themselves would likely break down, physiologically and psychologically. Physiologically. Total lack of natural sunlight means universal chronic vitamin D deficiency, unless it's perfectly supplemented forever. That leads to brittle bones, weak muscles, immune problems. Then there's the air quality. Even with scrubbing, you'd likely have buildup of trace contaminants, maybe chronic low-level oxygen deprivation, inducing severe oxidative stress, potential genetic damage over generations, widespread chronic disease.
And mentally, living in a cave forever.
Psychologically, it would be devastating. Humans evolved under an open sky, attuned to the rhythm of day and night, perpetual confinement, the sheer monotony of the environment, the lack of natural light. It's a recipe for epidemic depression, anxiety, psychosis, social friction.
Yeah, I can see that.
And imagine the societal structure needed to manage perpetually scarce resources and maintain absolute technological control. It would almost certainly have to be rigidly authoritarian, adding another layer of psychological burden. The human spirit itself probably couldn't endure it.
So it seems like every way you look at it, a long-term underground human civilization is just impossible. Geologically, ecologically, thermodynamically, technologically, psychologically. It fails on all fronts.
Pretty much. It's a fascinating fantasy, but it bumps up hard against the laws of physics and biology.
But here's the twist, the part that really, as I said, blew my mind when researching this. The core concepts behind this failed fantasy for Earth, they're actually driving the real scientific search for life elsewhere.
It's this incredible paradoxical connection, isn't it? The idea of a habitable zone, shielded from a hostile surface, possibly powered by non-solar energy. That's exactly what astrobiologists are looking for on other worlds.
It's like the question we asked about Earth is the right question, just for the wrong planet.
In a way, yes. There's even this thought experiment called the Silurian hypothesis, basically asking, if an industrial civilization existed on Earth millions of years ago, like the Silurians in Doctor Who, would we find any evidence?
And the answer is
Probably not. Geological processes would erase most traces. It makes you think about how alien Earth's own deep past is and primes us to consider life hidden from view.
So why is the subsurface the new frontier for finding life out there?
Because for many planets and moons in our solar system, the surface is just brutal. Intense radiation, extreme temperatures, no atmosphere to speak of. The subsurface offers potential protection.
Like a shelter.
Exactly. Shielding from radiation, insulation from wild temperature swings, and critically, the potential for stable liquid water, which seems essential for life as we know it. And Earth's own deep biosphere, powered by chemosynthesis, gives us a template for how life could exist down there.
Okay, let's take an example. Mars, red planet, looks pretty dead on the surface.
Right. The Martian surface today is blasted by radiation-thin atmosphere, no global magnetic field, but we have tons of evidence that ancient Mars was warmer, wetter, had lakes and rivers, if life ever got started there.
Its best chance would be to retreat underground.
That's the leading hypothesis. The subsurface would have offered refuge as the surface became hostile, and amazingly, recent data from NASA's InSight lander, using seismology just like we do on Earth, it actually suggested the presence of liquid water today, maybe 10 to 20 kilometers down beneath the Martian surface.
Wow. Seriously, liquid water now.
The data points that way. So the search for Martian life has shifted focus dramatically. Scientists are now seriously targeting the possibility of a deep, subterranean, potentially chemosynthetic biosphere on Mars.
Okay, Mars is one place. What about those icy moons out past the asteroid belt? Europa keeps coming up.
Europa, orbiting Jupiter, is probably the most exciting target for this kind of inner-world life. Beneath its thick crust of water ice, we're almost certain there's a vast global ocean of salty liquid water.
An ocean under the ice. How much water?
Potentially more than twice the volume of all of Earth's oceans combined. It's huge.
And the ice protects it.
Perfectly. Shield it from Jupiter's intense radiation belts. And the ocean stays liquid because of heat generated by tidal forces. Jupiter's immense gravity constantly squeezing and stretching the moon.
So protected water and heat. Sounds promising. Could there be energy for life?
That's the billion-dollar question. Scientists theorize there could be hydrothermal vents on Europa's ocean floor, much like the black smokers we find in Earth's deep oceans.
Which are teeming with life here.
Teeming with chemosynthetic life, yes. On Europa, chemical reactions between the water and the rocky seafloor processes like serpentinization could produce hydrogen and other chemicals, providing the energy needed to fuel a completely self-contained, sunless ecosystem in that hidden ocean.
So we're sending probes to check this out.
Absolutely. Missions like NASA's Europa Clipper are specifically designed to fly by Europa, study the ice shell, sample any plumes erupting into space, and assess whether that ocean truly could be habitable.
It really is this incredible inversion, isn't it?
It truly is. The idea of an inner Earth fails because our planet's main habitable zone is the surface, bathed in sunlight. But for places like Mars and Europa, the surface is hostile, and the interior offers the most plausible refuge for life.
The fantasy framework for Earth becomes the leading scientific hypothesis for these other worlds.
Exactly that. It's quite a remarkable turn.
And that really brings us full circle on this deep dive. We started with this captivating, enduring myth of a civilization beneath our feet. But the science, the geology, the physics, it's absolutely definitive. Earth is not hollow.
Nope. Seismic waves, density, how planets form, how rock behaves under pressure, our magnetic field, plate tectonics, multiple independent lines of evidence all point to a solid, layered interior.
And while we do have these incredible giant caves like Mammoth and Sunawang, they're geological wonders, yeah, but they're nowhere near the scale needed. They're orders of magnitude too small and fundamentally limited by geology to house a civilization.
They simply can't provide the stable, vast space required for a self-sustaining biosphere.
And even if, magically, Such a space existed. The sheer engineering and thermodynamic challenges of maintaining a closed system for millennia, it's insurmountable. The waste heat trap, the energy demands, the waste disposal, keeping technology running, just keeping people sane and healthy. It's a cascade of unavoidable failures.
The whole concept collapses under scientific scrutiny. It's just not viable.
But, and this is the cool part, the reality science has uncovered is arguably far more wondrous than the myth. Earth isn't hollow, but it is teeming with hidden life.
That deep biosphere, those extremophile microbes surviving kilometers down, powered by chemistry, it's completely revolutionized our understanding of biology and the limits of life itself. It shows life can exist in places we never dreamed possible.
And incredibly, that very framework, the idea of a world within, shielded, potentially habitable, which has failed for Earth, has become our prime guide for finding life beyond Earth.
It's the leading edge of astrobiology. The fantasy of inner Earth is impossible here, but the serious scientific hunt for life within Mars, within Europa, within other icy moons, that's where the excitement is now.
So maybe the final thought for you listening is this. What possibilities does this profound inversion, where our planet's impossible fantasy becomes the leading scientific hypothesis for life on other worlds, open up for how you think about life beyond Earth, and maybe even the hidden life still being discovered right here on our own planet?